All right, everybody. This is the last in our series of gas law videos, and this one covers the ideal gas law. Now, the ideal gas law is going to serve as a really great transition into our next unit, because the next unit is going to talk about why the amount of a substance really matters, and that's the other variable that we're bringing in here. So we're pretty familiar with the effects of pressure, volume, and temperature on gases. And we've talked about a lot of situations in which that really matters. But we haven't yet talked about the effect of the amount of gas. And it's pretty logical to think about. For instance, if you pump air in a tire, you're not changing any other property except for the amount of the gas. So when you increase the amount of the gas, the volume increases, so a balloon gets bigger when you blow it up. The pressure also increases because there's more particles pushing up against the side of the container. And that is a really important factor to consider that we haven't yet considered yet because we didn't have the equation to do it. Enter the ideal gas law equation. So you can see here in front of you the ideal gas law equation. It is PV equals nRT. And so I've kind of broken it down here and talked about what each of these quantities mean. And when you do your problem set for this week, you'll have a couple examples that show you these different variables. So P is obviously the pressure. We're pretty familiar with that. The difference here is that where the units didn't really matter as long as they were the same on both sides in the previous equations, they really do matter here. And so here the pressure must be in atmospheres. And if you look up to the right corner of your screen, you see a couple conversion factors that are going to help us get pressure in atmospheres. So if we're given a pressure in millimeters of mercury, for example, which is a pretty common unit of pressure, the unit that we see on barometers that measure air pressure, for example, then we're going to take that number and divide by 760 to get a value in atmospheres. And 1 atmosphere is also equal to 101.3 kilopascals, which is actually the official scientific unit of pressure. And so we'll need to divide that pressure, whatever it is, by 101.3 to get the pressure in atmospheres. And so as long as we have the pressure in atmospheres when we plug it into the equation, we're good to go. V is obviously the volume, but V in this case must be measured in liters. And usually the only other unit you're ever going to see is milliliters, and so you divide that number by 1,000 and you get the number in liters. That one's pretty easy. N is the number of moles. The mole is the unit that we use to measure the amount of a chemical substance. In this case, since we're dealing with gases, we're talking about the amount of a gas. R in this equation is a gas constant, and that is a constant that allows us to kind of put all these units together. In this case, the units don't really matter that much when we're putting them in the equation. Often they can be distracting, but the value for R in all the problems that we're going to do is 0.0821 liters atmosphere per mole Kelvin. Again, those are just the units of that gas constant. And the number here is what really matters. And I will provide that to you in any problems you might need to do. And of course, temperature, T, is always in Kelvin. If you have the temperature in Celsius, add 273, you get Kelvin. I don't think I need to review that with you by now. You're pros. Okay, so on to our problem. So a tank of gas is kept at a pressure of 1,500 kilopascals and stored in a walk-in freezer at a temperature of -4 degrees Celsius. If the tank contains 4.25 moles of gas, what is the volume of the gas inside the tank? So the first thing we always do in these problems, we're going to know 3 of the variables, and we already know R. So the trick is to figure out what we don't know. In this case, it asks you what is the volume. So what we're solving for here is V. So that must mean that we can figure out all of the other variables. So we'll start with P. So P is given as 1,500 kilopascals. And you may remember that it's really important that we have the pressure in atmospheres. So we're going to need to use our conversion factors and convert to atmospheres. Now, Dimensional analysis is our friend here. Remember, dimensional analysis is all about just canceling units. You may instinctively see that you need to divide here by 101.3 to get the value in atmospheres, and that's 100% fine as long as you put the correct unit in the problem. I'm going to be a little forgiving on the dimensional analysis for now, but you can see here that we're able to cancel out kilopascals, and the math we're going to do is 1500 divided by 101.3, which will give us 14.8 atmospheres. And so now we have the pressure in the right units. We have volume that we're trying to solve for. We're given N as 4.25 moles. You'll often see me abbreviate moles, MOL. R is 0.0821. Again, I'm just putting in the number here, and you're welcome to do that as well. And temperature, of course, we need to convert to Kelvin, so we have negative 4 degrees Celsius, and we add 273 to get 269 Kelvin. So we're just going to go ahead and plug in these numbers. I'm going to use a different color for that just to mix it up. And we're going to have 14.8 times V is equal to 4.25 times 0.0821 times 269. So, to solve this, it's going to be pretty simple. On the left-hand side, you have 14.8 times V, and I'm just going to go ahead and put those together. And if we multiply all three values on the right-hand side of the equation, we get, and I tend to put in exactly what I get from my calculator, and what I get from my calculator is 93.860825. And the reason I do that is because typically you're going to do that math, you're going to multiply those three numbers together, and then you're going to finish the problem by dividing. So you want to avoid rounding until the end of the problem. As a rule of thumb, we're going to round to 3 sig figs here, pretty much always, unless I tell you otherwise. So in this case, we're going to divide both sides by 14.8. And the volume is what we get when we do that division, which is 6.34 liters. So if we were to measure the amount of space that gas took up inside that tank, it would be a volume of 6.34 liters. So that one ran a little long. Sorry about that, but I think the explanation at the beginning will be helpful, and hopefully you can see how all of these things fit together, how the units really do matter here, and I hope that's helpful. Have a great week.